This video covers the Pivot Optimiser use case of the Shockwave Engineering IoT ecosystem. The primary purpose of the Pivot Optimiser is to control the pressure on center pivots to reduce energy. It also allows the operation of the pumps to be automated, saving management intervention. A remote pressure monitoring station is installed at the center and end of each pivot. These stations transmit the pressures over a radio link to the main unit over here, which is installed in the pump house. This main unit sends a speed signal to a variable speed drive, which is installed here. The variable speed drive then speeds up or slows down the pump to get different pressures at the center and end of the pivot. The main unit receives the center and end pressures over a radio link and compares those pressures to their required set points. If the pressures are below the set points, it increases the speed of the pump. If the pressures are above the set points, it slows down the speed of the pump. The objective is to make sure that one of the pressures is at the set point while the other pressure is above the set point. So for example, if the pivot is facing uphill, the lowest pressure will be at the end of the pivot, so the system will control the end pressure. When the pivot is facing downhill, the lowest pressure will be at the center of the pivot, so the system controls the pivot center pressure. By keeping both pressures at their minimum set point or just above the set point, the least possible energy is used. In addition, it assists the pivot with maintaining a uniform distribution of water. In addition to the primary function of controlling pressure to save energy, the Pivot Optimiser also performs other monitoring, protection and automation functions. The system monitors pump inlet pressure. If the inlet pressure gets too low, then the system will send a warning to the operator. If the pressure gets even lower, then the system will shut down the pump and alert the operator to the fact that the pump is shut down and the inlet needs to be unblocked. The system also monitors the pump outlet pressure, power consumption by the motor, and flow rate through the pump. It uses these parameters to calculate the hydraulic power, which is the differential pressure multiplied by the flow rate. It then divides that by the electrical power that's consumed by the motor to calculate the overall pump and motor combined efficiency. If the efficiency is very low, then we can perform further analysis to determine the root cause of the low efficiency. Low efficiency can be caused by an incorrectly sized pump or by a worn out pump. During startup, the Pivot Optimiser limits the variable speed drive speed according to a logarithmic curve. This is different to all other VSTs, which allow either a linear startup or an S-curve startup. The advantage of a logarithmic curve is it speeds up the VST quickly in the beginning, allowing flow to start, but as the speed gets higher, it reduces the rate of increase, which limits the flow rate and prevents too high a flow rate going through the pump, which can damage the pump and exceed the current limits of the motor. The Pivot Optimiser limits the maximum flow rate, pump outlet pressure, and power consumption during all operating conditions. This prevents excessive pressures which may damage pipeline, excessive flow rates which may damage the pump, and excessive currents which may damage the motor. The minimum pump outlet pressure and minimum flow rate can also be set. The Pivot Optimiser allows the pump to be started either from the pump house or from the pivot over a wireless link. This eliminates the need for a communication cable from the pivot to the pump house. The pump run command from the pivot control system is also monitored, allowing the pump to be shut down if the pivot gets stuck or goes out of alignment. A single Pivot Optimiser will control one pump, which can be running 1, 2 or 3 pivots, either running individually or running at the same time. To maximize energy savings, it is best if the pivots are run individually. The system will also control the pressure of permaset or pod irrigation systems. A single pressure monitoring station is installed at the furthest and highest point in the pod or permaset system. This allows a constant pressure to be maintained at the nozzles, even if they are very different block sizes. Different block sizes usually result in different flow rates, which result in different pump outlet pressures and different pipe friction. By controlling the pressure at the nozzles, we manage to ensure that there's a uniform flow rate throughout the pod or permaset system. The energy saving is highly dependent on the change in elevation from the pump to the pivot center, the variation in pivot elevation, and the excessive pumping pressure. We typically expect a direct energy saving of 25%. In some cases, we've achieved energy savings as high as 40% from direct pressure control. In addition, when we analyze the data that the system is monitoring, we can then optimize the overall pumping system. This includes changing the pump and motor as well as pipeline. When we optimize the entire system, we achieve savings between 50 and 75%. We have found numerous systems where there is insufficient pivot pressure. This results in poor water distribution and inefficient irrigation. In these cases, we first have to increase the pumping pressure, which uses more energy, but that results in a higher yield of the crop.